Rahim. So we have a course probability and statistic for engineers. Today's lecture number 10, and the topic is exponential distribution. We are already discussing different type of probability distributions. We have already discussed constant distribution, binomial distribution, Poisson distribution, and now we are going to discuss exponential distribution. As I have already mentioned that all these distribution depend on the type of data. So for exponential distribution, the data has to be continuous data. So exponential distribution basically work when the data is constant. So when the data is continuous, while previous distribution that was discussed about the distribution that we have discussed previously was Poisson distribution, and the data in that distribution was discrete data. In every kind of distribution, we first have to check whether the data is continuous or discrete. So for exponential distribution, the data will be continuous data. Now, coming towards exponential distributions, the exponential distribution provides probability models. In fact, these are probability models, or we can just probability distribution, that are very widely used in engineering and sciences and other applied sciences. In engineering, not specific to the civil engineering, but we can use it in electronics. We can also use it in mechanical engineering. I have one example here that is related to the civil engineering, so I will discuss later in the slides. Exponential distribution is frequently used as a model for the distribution of times between occurrence of successive events, such as customer arriving at a service facility. So basically, in exponential distribution, we have let me have a new slides, and just I will show you how exponential distribution work. Let's say we have x-axis and y-axis, so we can take two different axes. Let's have this color as not the outline, that will be make it white, and we can draw two axes. So first axis, okay, make it let's make it outline of the geometric black. Okay, so that is y-axis, and we can take another axis, that is x-axis, from here to here, and give it black color. So if we have to excuses for the line that is not clearly, okay, that is not very much okay. So if we have probability distributions on probability distribution p of x, probability distribution on y-axis, and we take x-axis as a random variable x. So we will be having x as a random variable on x-axis, and we can take its respective probability on y-axis. So point to note that the random variable in case of exponential distribution is continuous, so that x might be the time. So time is one of the continuous data. We might have some other values, but we cannot take number of people, number of cars, number of buses, or anything else. So in that case, in case of exponential distribution, on x-axis we will be having a continuous data, and the graph for exponential distribution, it will be somehow like this. Let me try. It will be somehow like okay, let's try again. Okay, so if I draw a graph, it's not easy for me to just draw a graph, use these tools. It's very hard, but I'm trying to use it. So exponential distribution, the graph will be somehow like this. And I'm not using the bars in that case. I'm using the line because if there is a time value, if that is, for example, if time value is equal to on x-axis is equal to 2.5, so that's also fine. Any value on x-axis time value 2.5, maybe somewhere here, so that will be having a value of px. So just remember that in case of the Poisson, in case of the exponential distribution, we will be having continuous data. That means 1.5, 1.75, 1.8, 2, 2.5, this kind of data. And for that data, we cannot use the bar. We cannot plot it in the form of bars, but we have to use a line graph. Now, okay, so the probability density function for exponential distribution is fx. Okay, let's try that one. The probability density function for exponential distribution, if I write it here, that will be equal to, let me copy that and write it here. The probability, okay, make a smaller one. Okay, let's try something. Okay, I have already explained that, so I will delete that one. I will delete that all, or I can use another slide for that. So the probability density function for in case of exponential distribution, that will be small f. Probability density function equation. Probability density equation. Smaller f with the value of x that is equal to lambda, multiplied by exponential, okay, lambda multiplied by exponential e, and to the power exponential to the power minus lambda x. So that is the equation for the exponential distribution function. So if we have exponential distribution, we can call it exponential function. So that will be the equation, and in that equation lambda is same rate of occurring of event that we have already discussed last time in Poisson distribution. That is also the parameter of exponential distribution, and x here is representing the random variable, so that x is not a discrete one here, but that will be a continuous. Same equation. So lambda e to the power minus lambda x is the function of probability distribution, for which the x should be larger than 0. That shouldn't be 0, that should be larger than 0. Okay, 0.1 is fine, but not 0. For definition is x is said to have an exponential distribution. X is a random variable that is said to have an exponential distribution with a parameter value lambda. I have already discussed in other lectures that every distribution will have a specific parameter. So that parameter for exponential distribution is lambda, which is the rate of occurrence of an event, and that parameter is also same for the Poisson distribution. If the probability density function PDF of x is that lambda e to the power minus lambda x. Now let me remove these slides. Delete slides. Okay, how about the expected value and variance of exponential distribution? So before discussing that, I will also mention here that we can also write exponential distribution as fx is equal to 1 divided by beta e to the power minus x divided by beta. So that beta is same inverse of lambda. If you see here, beta is equal to inverse of lambda, and as you know that lambda is actually the rate of occurrence of event. So that is a rate. The inverse of that, inverse of the rate will be time. So beta is the mean time interval between consecutive events. uh, you can also use lambda if you try to solve the exponential distribution function, and you can also take the inverse of that for the exponential distribution. You can either use lambda or beta. Now coming to the expected value and variance are the, I can say, mean value and variance of exponential distribution. That is, if x is exponentially distributed random variable, so the mean value is 1 minus lambda, and variance value is 1 divided by lambda square. So the mean for Poisson distribution was lambda, variance for Poisson distribution was also lambda. Here in case of exponential distribution, mean of exponential distribution will be 1 divided by lambda, variance of exponential distribution will be 1 divided by lambda square. Similarly, we can also express that in the form of expected value, that is the mean value is equal to 1 by lambda and variance is equal to 1 by lambda square. Now coming to different shapes of exponential distribution, as I have already discussed about that the shapes of distributions depend upon its parameter value. So as I have already told you about Poisson distribution, that the shape of Poisson distribution changes if you change the value of lambda. I will also discuss same kind of Excel sheet with you as I have discussed last time. For the Poisson distribution, I will develop a exponential distribution curve in case of exponential distribution when we have different value of lambda. Now you can see here, when you have lambda is equal to 2, when you have lambda is equal to 0.5, when you have lambda is equal to 1. So you can see that as the lambda value varies, the shape of exponential distribution also varies. That first curve is for the lambda is equal to 2, then you have for lambda is equal to 0.5, then you have lambda is equal to 1. And you can see here that the steepness of distribution, the steepness of exponential distribution, that changes with the change of lambda. You can see here that when lambda is equal to 2, so when as the value of x increases, at lower values the values all same, but as x value increases there is a sudden change in the value, and then it become constant value. While in case of lower value of lambda, the lower values all are changing almost at a constant rate with the value of x. So that lambda basically represent the shape of exponential distribution, as other parameters have already expressed the shape of their respective distributions. So as I said about exponential distribution, the probability density function of exponential distribution in this slide, we can see these are all the probability density functions of different kind of exponential distribution on the basis of their parameter values. But if we talk about the cumulative density function, the exponential distribution, that can be probability density function that can be integrated. If we take the integration of this, if we take the integration of this equation, then we can determine the cumulative distribution function, and the graph for cumulative distribution is somehow like this. So we have a y-axis that is representing the cumulative distribution functions of exponential distribution, and we have x value that can represent the time, that can represent other continuous variable. So as the x value increases, the value of cumulative distribution function also increases. We use capital F for cumulative distribution function, and we use the small f for the density function. And the equation for cumulative distribution function is 1 minus e minus lambda x, keeping the x values larger than 0. Now using these functions we can solve a problem if we have data that is exponentially distributed. So we can use exponential distribution and check the probability values of a different value of random variable. Now there is one example that has been taken from a journal paper, that is probabilistic fatigue evaluation of riveted railway bridges, Journal of Bridge Engineering in 2008, that has been published. That suggests that exponential distribution with mean value of 6 megapascal as a model for the distribution of stress range in a certain bridge connections. If you have a bridge connection and you perform different tests on that to check the distribution of stresses, so someone has already done that, maybe the author of this paper, and they found that the values are exponentially distributed with the mean value of 6 megapascal. So we have expected value here. We have expected, if you see toward the solution, let's assume that this in fact the true model, then Ex expected value, that is 1 by lambda, is equal to 6. So we have the mean value of data when you have exponentially distributed when you have exponential distribution. Now from this equation we can take lambda is equal to 0.1667. You have already mean value and you can compute lambda value from this equation. Okay, what is the probability that stress range is at most 10 megapascal? You are going to determine the probability of stress ranges range that is at most 10 megapascal. And what is the probability that the stress range is between 5 and 10 megapascal? You can see here that the data that is continuous data, that is not discrete one. So we might have a mean value of 6.6, or we also have, and if someone determine the stress values at a bridge connections or any other for uh, any other parts of bridge, he will not get exact value of stress, that is 6, 5, 5, 6, 7, 8, 9, 10. So the value might be 5.5, 5.6, 6.5, something like this. But after computing that values, they have determined that mean value is 6, and they are going to check that what is the probability that the stress range will be at most 10 megapascal, and what is the probability that the stress ranges will be between 5 and 10 megapascal. Now if we solve that, the probability that stress range is at most 10 megapascal, that is equal to probability of x smaller r equal to 10. We have to determine that all the probability values at for x smaller than 10. We will be having the probability value of px is equal to 0, then px is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we also have to determine the probability value of, for example, probability of x is equal to 0 0.5, 0 0.75, 0 0.85, because we have all these data is continuous data. So the best way is for determining that the probability value for x smaller than or equal to 10, that is equal to 1 minus e to the power lambda x. X value here is 10. So as we have at most 10 megapascal, x value here is 10. Lambda value we have already discussed in the previous slide, that is equal to 0.1667. So at most we will be for the 10 megapascal. By using this equation we can determine that the probability value is 0.811. So most of the data which they have already computed, or the data that was lesser or equal to 10 is 81%. We can also see for the probability that stress range is between 5 to 10. If we check that one, when the stress value is between 5 to 10 megapascal, so we can use this equation, probability of 5 less than or equal to x less than or equal to 10. We will determine all the probability values that are between 5 and 10. We can use this equation. We can use the same equation when we have probability value. Let me Okay, when we have the probability, that is for the probability of 10, and that is the for the that is this is basically the cumulative distribution function when you have x is equal to 10, and that is the probability cumulative distribution function when you have x is equal to 5. So when you subtract the cumulative distribution function of 10 of 5 from the cumulative distribution function of 10, and then you will get the probability value between these function. Let me draw that and explain that. Okay, we have on x-axis we have this one, then we can use y-axis, sorry, that is for the y-axis, then we can use x-axis. Okay, x-axis we have the stresses value on x-axis, and we have probability value on y-axis. If I take the probability of the cumulative distribution function, so the cumulative distribution function will be somehow like this. Okay, now if we talk about that, let's say we have this value for 5, this value for 5, this for 5, and this for 10. If we have okay, let me draw it straight. So we have two different values. Maybe the lower vertical line is representing random variable 5, and the upper is representing random variable 10. The probability, respective probability value for 5, and same respective probability value for 10. Now this whole region, if I shade it, I'm not sure if I will be able to shade that. Okay, it's not possible for me to shade this region, but you can see the cursor. This region, that is representing 0.246, because that is the this whole region represent probability of x less than 10, and this region below that lower line, this region is representing probability of x is equal to 5. So when you take the when you subtract that region from this whole region, that will give you the mid value, that will give you the probability value between 5 and 10, also including the value of 5 and value of 10. So that region, that whole region is copy, and if I cannot paste it here, but I will say that this region, you can see the cursor, this whole region is representing 0.246. Now there is another example. You can also read that and you can solve it by yourself. Let me explain, or let me draw some exponential distribution curves on Excel. Okay, if we have different value of x, that is random variable, let's say 1 2 3 4 sorry 3, that range from 1 to let's say 15. Now this is not wholly representing 1 and 2. This random variable is continuous, so 1 and 2 have the mid value between 1 and 2, maybe 1.5, 1.75, 1.25. So we will also consider all these values. Now probability value of x, we have to determine the probability of respective value of x, and we have lambda. We have a lambda, let's say lambda is equal to 0.5. Let's say we have lambda value 0.5. If we determine the probability value of respective x value is equal to, that is exponential, we have to use exponential distribution. For exponential distribution, we need respective x value, and we need lambda value, that is 0.5 here, just an example, and I'm taking lambda value 0.5. We have to fix that 0.5 because we have to take every time for every value of x. Now let me fix that. I'm not going to determine the cumulative value. I'm just determining the density value, so I will take it false. Now 0.303 is the exponential distribution or exponential distributed value, probability value for 1 when you have lambda is equal to 0.5. And if you take it till 15, that will give you different value of exponential distribution for different value of random variable. Let me plot that. If I plot, I have to use the line graph here because the data is continuous. If I take the line graph, now you can see here the exponent for the exponential distribution. When you have x value on x-axis, random variable value on x-axis, and you have probability values on y-axis, using a lambda value 0.5, and we will get the curve like this. Now here we also can check the value. Let me check that if I can take some lines. If I take them, okay, not that one. Okay, so you can see here that it's not only giving me the value for x is equal to 1 or x is equal to 2 or 3. It's giving me value for x is equal to 1.5, 1.75, 1.25. There's also giving me value for 2.2, 2.3, 2.5, 2. That's not like Poisson distribution. That is similar to the Poisson distribution, but that is taking different value of random variable that are all continuous. Now that is the probability density function when you have exponential distribution. Let me change these values, and instead of probability density values, density function, I will use cumulative distribution, and I have to take true here. Now if I use this and drag that to 15, and that will be increasing curve starting from the lower value of probability on y-axis for 1, and that will increase, and as I said, that sum of all probability will be equal to 1, and that will finish at 1 here for 15. Now you know that the shapes of the probability distribution function also varies with the value of lambda. If I go toward the previous graph and change value of lambda, let me change that 0.5 and make it 1, so the graph will change. If I take it 0.1, so that will also change. Now let me explain here that if we decrease value of lambda and value of lambda become very small, so that exponential distribution will become a straight line. So exponential distribution is so that's becoming a straight line. A linear graph is a type of exponential distribution when you have lambda value very much small. Now if I take it 0.05, so you can see here that the curve graph that is now changing, and that is becoming a straight line. So as you decrease the value of lambda, the exponential distribution will become equal to linear distribution, or it will become not a linear distribution, but it will give you a straight graph, a straight line. Now that was all related to the exponential distribution. There are different type of exponential distribution as well, but that are all at higher level. We also have hypo exponential distribution, we also have hyper exponential distribution, we also have phase type distribution, hypo Erlang distribution, we have a normal Erlang distribution. These are different classes of exponential distribution. I'm not discussing it here because that is not a part of your course, but you can study or you can read more about exponential distribution from different books. If you have any problem related to the exponential distribution or any other previous lectures, you can discuss it with me. Now you can use the same technique to solve example number 2. That was all for exponential distribution. Thank you.